Great. Well, thank you very much. It's occurred to me that most people, if they're relatively well-adjusted, have already rationalized why what they did was the right thing for them to have done, which is a very good coping mechanism. But then the problems start when that starts to get integrated into the advice that people give to young people, because I can appreciate as a scientist, life is not what we would call a controlled experiment. I had one mother, I went to one school for university, etc. So I'm really only guessing what things actually did matter or not, what circumstances did matter or not, but I'll make my best guesses. So the first is I was born in 1957, which I know is unimaginably long ago for many of you, but that was the year of Sputnik. And so growing up in the United States, science and engineering were celebrated. There was robust bipartisan support for science education, scientific research, and like a lot of boys my age, and sadly it was mostly boys back then, I had a chemistry set and I had a little toy microscope that I recently donated to the Nobel Museum, and I had electric cars and trains and all sorts of things that sort of fostered an interest in science and engineering, whether you knew it or not. Now, I did like science, but I must say I did not like studying, so I was a pretty undistinguished student for most of elementary school and most of high school. And looking back, I've sometimes said that if you're bored in school, that might be a very bad sign, but it might also be a very good sign. And in hindsight, I was simply bored. But then when I was about 16, my high school got a computer terminal that was linked to a mainframe at a neighboring university, and this absolutely changed my life, because I mentioned I wasn't a distinguished student, but there was an asterisk. So the asterisk was I was always really good in mathematics because it came easily to me, and to me there was no rote memorization involved. You got the concept and you didn't need to study, and you could do well. So fortunately, without studying, I'd always done very well in mathematics, and now we had this shiny computer terminal, and this seemed like mathematics brought to life, and it sort of captured my imagination. So I would sit there and write code, and then one day I looked in the waste paper bin and there was a pamphlet. I can still remember it because it was orange with green lettering. It was pretty ugly. But it was a pamphlet for a National Science Foundation student science training program for 32 gifted high school students in mathematics or computer science to go down to Florida Atlantic University and take college level courses for the summer. So I applied, and remarkably I was accepted, and so I went to this course, and this completely changed my life. So the first thing was, it was the first time I was really taking courses that I found really challenging and where the students were so stimulating, they were so brilliant. And I'd never had this experience before, and so I decided I actually liked school if the material was challenging and I was surrounded by really smart people. And over the years I've learned that I grow the fastest when I'm surrounded by people who are smarter and more talented than me. The other thing was I was pleasantly surprised that I could hold my own amongst these 32 students, except for one student who was just head and shoulders smarter than me. But that's a good lesson, because almost invariably there's somebody out there who's smarter than you are. And in fact, I decided that summer, okay, he's going to become the academic mathematician. I better find something more practical like medical school, because there's a whole other gear that I don't have. Now, ironically, he went on to be a clinical doctor also. In learning more about these students, however, not surprisingly, as I said, I could hold my own with them, but they all had far better grades, and I learned that's because they actually did their homework, and they did the extra credit problems, and they sat in the front of the classroom, etc. So I decided, okay, I'll try to do that for 1 year. This is my remaining year in high school, my senior year. And so I became a so-called late bloomer. And unfortunately, today it's more difficult to get into an elite school, such as in Oxford, if you're a late bloomer. But back then, you still had a chance. And so I did go to college with the thought that I'm now going to go to medical school. I did major in mathematics for the reason I've already given you. That, at least that part came relatively easy. And I also majored in chemistry, thinking I might want to be a pre-med. And then as I was finishing college, one of my fellow students said, if you want to apply to medical school, you really want to work in a laboratory. That looks really good on your application. So I met with a physical chemist who parenthetically graduated from Cambridge. I'm sure the problem I'm about to tell you wouldn't have happened if he had graduated from Oxford, but he was a Cambridge grad. And he told me that he had 7 undergraduates work on this particular research project before me, and all of them had gotten into medical school. So I went skipping out of his office thinking I had found the golden ticket to medical school, and I signed up immediately. Now, if I had been smarter and wiser, I would have said, I wonder why these 7 previous students couldn't bring this project to completion. And I became the 8th student who couldn't bring the project to completion. Moreover, I did learn from a discussion with a visiting professor that this project was never going to be completed. I've sometimes said that this was the perfect storm for a young person. That in hindsight, I will tell you the project was uninteresting, unimportant, and undoable, which is a really good way to extinguish a young person's career in the lab. And I had the audacity during my last lab meeting to actually more or less say those 3 things. I didn't say it quite that way, but that was the message I was trying to convey. And so to reward me, he gave me a C- for laboratory research, which for a pre-med is like having a wooden stake driven through your heart. And then, as an added flourish on the side of my transcript, he wrote, "Mr. Kaelin appears to be a bright young man whose future lies outside of the laboratory." So that was my introduction to laboratory research. Despite this scarlet letter, I actually did get into medical school, but now it was a single-minded focus that I was going to be a practicing clinical doctor and not a lab researcher. And I had the good fortune to go to Johns Hopkins to do my clinical training, where I not only met my wife first and foremost, I also started to learn about obscure diseases like a very rare hereditary cancer syndrome called von Hippel-Lindau disease. So, I was saying to the students a moment ago, I've been impressed over the years how many times I've learned something for one reason, and then years later it helps me in some completely different way that I couldn't have anticipated. So I became fairly knowledgeable as a clinical doctor. I went to the Dana-Farber Cancer Institute to become a medical oncologist, that is a doctor who specializes in the clinical care of cancer patients. One way you can become board certified in medical oncology is to spend 2 years in a laboratory. And so with great trepidation, I said, maybe I'll at least go into a lab with the thought that even if I'm not going to do this, I can at least watch how it happens, because it was very clear now by the late 80s that there was about to be a revolution in medicine because of modern molecular biology. So I picked a very junior, very nice faculty member who had just started his own laboratory. I thought it would get a lot of individual attention because it was him, his technician, and me. And after about 4 months, he called me into his office and said, "I don't know how to tell you this, but I just can't do this anymore. I'm going to shut the lab down." So I thought this was another bad sign in terms of my future scientific career, that not only were people telling me I shouldn't do science, but apparently I could extinguish other people's careers at a distance. Like there's this zone of inhibition. If you get too close to me, your scientific career is over. And so I found myself as a refugee at that point. I needed a lab for 18 months, and I had the good fortune, through dumb luck, to find David Livingston. And if everything was wrong in my first lab, now everything was right. I had an outstanding mentor, an outstanding and doable project. I had great colleagues, great people in the lab to help me. So I guess this is the closest I can come to a control experiment, because I initially randomized to a dysfunctional laboratory, and then I randomized to a functional laboratory. I think I was the same person, but there were very different outcomes, obviously. And then in 1993 or 1992, I started my own laboratory. I was looking for something to work on that would distinguish me from my former mentor. And I picked up a scientific journal, and there was the gene that caused von Hippel-Lindau disease. And I knew from my clinical training that this could be a Rosetta Stone for studying things like kidney cancer and for studying things like angiogenesis, how tumors get their blood supply. And finally, that this would be a Rosetta Stone for understanding how cells and tissues sense and respond to changes in oxygen. And one thing I think both Peter and I completely agree on is, first and foremost, every experiment or line of investigation really starts with the question. And if you start with a good question, you're more than halfway there. And so if I was to give myself credit for one thing, it was having the instinct that the VHL gene would be a good way to start to understand things like oxygen sensing. So I'm going to stop here. I look forward to your later questions. Thank you.
Thank you very much. It's a great honour to be here to talk to you this evening. And I'd like to tell you a little bit about the work, at least as I understand it, and a little bit more of the personal story as to how I came to be here from a position 30 plus years ago of intending to be a physician in the National Health Service. Quite a long and tortuous journey. As Bill said, the work concerns the sensing of oxygen levels in oxygen homeostasis. That's a control, for those of you who are not scientists, that's a control process akin to the operation of a thermostat in the control of heating. And at least this is my version of what we found out. Two things, that the system exists in all cells, that was not fully understood, and how it works. That's an enzyme, a biological catalyst that splits dioxygen, O2, and uses one atom of oxygen to mark a protein and flip a switch, which signals for the responses that are made in response to the oxygen availability in the cell to control that homeostasis. So it's quite a simple thing, really. As Patrick Enforce, who was one of the judges in the Nobel Assembly, put it when he spoke to us in Stockholm, is obvious. Obvious that it would be in all cells, and obvious that it would work that way. It's a rather interesting way that he put it. Most things are, of course, obvious in retrospect, and I guess this is one of those. Presumably, the Nobel Assembly thought it was quite an important thing, and we're grateful for their thoughts on that. A fundamental physiological process and a complication, low oxygen, hypoxia, complication of most human disease. So you might say an important question to which ultimately there was a simple answer, at least at a certain level. Now, the most important thing in research is picking the research question. So I'll attempt to address two things. Given all the investment in biomedical research, how was it in the 1980s when we started that such a problem was left unsolved by others? And how was it that I chanced upon that problem? The problem of oxygen homeostasis is probably one of the first to be addressed by physiologists. Once the important principles of physiology were defined, the concepts of metabolism, homeostasis from Lavoisier to Claude Bernard. How did adaptation occur to unusual environments? People looked at altitude and knew that altitude was associated with hypoxia. So it was before chromosome biology, before the cell cycle, before DNA, yet not solved for a very long time. And I think the main difficulty was that question was in advance of the time. The difficulty was that people were looking at whole organism physiology, human physiology. We're now riding on that because it turns out to be important in integrative physiology. But conceptually, it's very difficult to deduce a mechanism across a highly heterogeneous integrated system, such as the human body or animal form. And it was that heterogeneity and complexity of different organs, different systems, that made it very difficult to deduce a molecular mechanism from, say, observation of the blood hemoglobin level or observations on respiratory rate and so on and so forth. And it was very difficult to intervene and draw a mechanistic deduction from that intervention. And as well, it's a difficult thing. Many of the things that were used to actually interrogate oxygen sensing would alter the level of oxygen. So I think people just got disillusioned with the failure of solution, the failure to understand this throughout most of the early 20th century, and it just dropped from fashion. Science has fashions, and it's bucking those fashionable trends that I think is very important, and this is part of the story. And so when I came to be looking for things to do, the EPO gene, the erythropoietin gene, that's a hormone that regulates red cells, had been identified by Jean Goldwasser, F. Kaelin at Amgen Corporation. A tissue culture model had been set up that enabled us to look at individual cells, not those complex whole organisms. That was Franklin Bunn. And this enabled a new molecular approach to the cell itself. But it was deeply unfashionable. I call my lab the hypoxia biology lab, and people used to organise tours around the institute. And when they ran out of time, they said, well, we don't need to see that hypoxia biology lab. It's not very important like the immunology lab. Had I called it the metabolic lab, it would have been much better. So for various reasons, it was, I think the problem was before its time, and then it became unfashionable. So what about me? Why did I come to that problem? Well, the interesting thing about winning the Nobel Prize is that it immediately appears to confer infinite wisdom. The phenomenon is quite odd, and even my children thought I had something sensible to say to them for the first time in many, many years. The first point I want to make in terms of me, and the Nobel Prize for that matter, is it's not necessary to be very clever to solve biological problems, and it actually might be a hindrance. So there are quite a lot of insoluble, complex problems were avoided on the simple principle that it was obvious, at least to me, that I wasn't clever enough to solve them, so I never even attempted a lot of things. The second important thing in a research question is not to follow others. I can be quite an awkward person. I hate authority figures, hate conventional wisdom, and sort of have an affinity for the alternative. And in terms of selecting a research topic, this is what I can tell you. You should never ever do what you're advised to do. In selecting, you should never do what you're told. So this is a bit like my experience of equity investments. By the time the advisors have got passed information from one to another, it's got to me. It's too late. The market's moved and I lose money. And the only way to make money, I guess, is to do the opposite of whatever you see me doing. But so you really by the time people are telling you to do something, it's a good idea. There'll be so many people in it, it won't work for you. So basically, at any one time, most people are working on things that are either intractable at that time or already discovered. And the summary of this part of the talk is that a combination of limited ability on my part and cussedness, unwillingness to accept professional norms enabled me to avoid those traps. And anyway, so those are reasons for not doing intractable things. What about the reasons for doing it? People are a mix of traits, and in other ways, I'm rather a passive person. I was so in my professional development. I studied medicine because the headmaster at school suggested it. That's all. I specialised in nephrology because a respected consultant I was working for suggested it. He said, Peter, I think you'd be good at nephrology and you can flatter anyone into anything, and away I went to have a go. I never gave either a great deal of thought. Unlike, well, I couldn't see that there was a big, it was going to go wrong, really, in a dreadful way, unlike addressing an impractical research subject. But there was a problem. The British Health Service is short of money, and it didn't want to employ too many expensive consultant nephrologist. So another person said, well, you want to be a nephrologist, Peter, you'll be lucky. There are only going to be 2 jobs between now and the year 2000. This is about 1980. That statement was massively wrong. There were lots of jobs, but it did sort of sharpen my mind. He said, you'll have to distinguish yourself in some way. And I didn't really know how that was going to be at the time. But people wrote case reports, and this, I think, was very important in shaping, in thinking of research ideas. It's much denigrated now. This means I wrote up a case that I'd seen on the ward, and when you do these, they're published in little journals. You have to sort of adjust your CV if you put forward for something like the Nobel Prize, and hope the jurors won't notice that your first papers were in these journals. You put them at the back of the list and so on and so forth. But there's one important thing about this. This involves looking across a whole range of patients like you people and spotting one that you can draw conclusions from the course of their illness. And this is a really good training for selecting a research topic. Which ones are going to be tractable? Which ones are we going to be able to draw a conclusion from what we see? So I actually think that was extraordinarily helpful in enabling me to look for something different that I thought was soluble. And that's really why I came to this question. But then, of course, there was also the issue of solving the problem as opposed to simply identifying it. And many things are not achieved by extreme talent, but by a mixture of qualities. So it's an interesting issue for consideration. Ballerinas, 100-meter sprinters, theoretical physicists. You have to have a particular type of body or mind, or it just won't work. Almost everything else is based on a mix of qualities. Believe everything, challenge nothing, you'll not go forward. Believe nothing, challenge everything, you'll end up in the police station. And so it was that balance that I think is important. So I've said you must have a new idea, believe no one, find your own idea. Then I think you do need to take advice. You need to take what's technically possible and respect those technologies. So I had the idea that I wanted to study EPO regulation, and then I did have a piece of good fortune. I had a friend with a lab, John Bell, and I had a friend with an institute, that was David Weatherall. And between them, they were able to introduce me to all the molecular techniques. There wasn't the slightest danger of going off into the massive field that John was researching in HLA genetics, or David was researching in thalassemia and hemoglobinopathies. So I went into those labs and that institute, and I asked everyone I could find what they thought I should do to solve that problem. And this is really, I think, for most of us, a secret of success, is getting the whole world to focus on your problem. There are all sorts of ways of doing that. It's a form of bullying, really, but actually we use all sorts of diplomatic tricks to persuade people to help us, and I had lots of people help me, and we eventually got there. It was an unusual career, I guess. I managed to do this and combine it with a lot of clinical medicine. About 6,000 admissions to the John Radcliffe Hospital, I'd estimate. After the Nobel, you face a lot of interviewers, and some of these thoughts, they're quite cheeky in a way, said, they thought this was rather odd. Really, if you're going to win the Nobel Prize, you should really focus on your job, which is the research. Some of the postdocs in the lab thought it was a bit odd. They thought it was dangerous that if they went to the John Radcliffe Hospital, they'd see professional doctors running around in green overalls, not myself. But it worked. And the question really, particularly for funders, is was this a complete fluke, or could it happen again? We can talk about that. I think there are no shortage of problems that are ripe for solution, and there are no shortage of people to solve them. But what we're saying is there need to be new problems, or unfashionable problems, and new people. And of course, in this circumstance, there's a major risk of non-solution, of not solving the problem. So the thing that I think we need to face rather squarely is the business of accepting risk in research. In the face of increasing budgets in research spending, the communities become rather risk averse. And this is fundamentally a contradiction in terms, I think. So I'll leave that with a message to those risk-averse people. If you don't like speed, you shouldn't fly fast jets. If you don't like risk, you shouldn't go near research. As simple as that. And this is a story which the ending is rather improbable from that position as an NHS consultant. And it did, I'm very grateful to them, entail the taking of risk by the Wellcome Trust, who funded me all those years ago. I'm grateful for them and grateful to you for your attention. Thank you.
So first of all, correct me if I'm wrong, but you began work on the topic for which you won the Nobel Prize separately, but won the prize together. Could you tell us a bit about what the different parts of your work together were and how they came together for the final result?
Yeah. So we had started working on this VHL gene that I mentioned in 1993 when the gene was isolated, and that was our path to trying to understand oxygen sensing. Peter, at about the same time, or even slightly earlier, had started working on the erythropoietin gene and how it was regulated as a path to oxygen sensing. And then, as you hope would happen occasionally in science, even though we started out working separately, I think our two lines of investigation collided with a paper that Peter published in 1999 that showed a connection between the VHL protein and another protein that scientists refer to as HIF, or HIF for short, which is a master regulator of EPO.
So from 1999 until 2019, for 20 years, did you work together on?
No, well, as Bill said, we started separately. To be clear, I started on this, what I've described as an unfashionable problem of EPO regulation. People said it doesn't really matter. We've got recombinant EPO, it's on the market. Why would you worry how it was regulated by oxygen? And the transition point for me was we did, it must be the simplest experiment that had the largest outcome. We found the control element in the EPO gene and we put it into cells that don't make EPO. It's an extraordinarily simple experiment. That's why I say, how was it that extraordinary simple experiment was not done in 1991 when we started? That showed that the system was across all animal cells, and that was my direction. And a little while later, Bill found the clue from the von Hippel-Lindau thing, and then we began to work sort of competitively, sort of together, and we clawed our way upwards to this oxygen sensor from that point. So it was a sort of two feeds in to what ultimately was a common route.
I think it's a very important question. So during the 90s, I would say we were sort of ping-ponging back and forth, building off of each other a little bit. And then, as I said, in 1999, the two lines of investigation collided. I had met one of Peter's trainees, Patrick Maxwell, at a meeting in Paris, and it was so clear the remaining big question was the oxygen sensing mechanism. And because they had helped us, hopefully we had helped them, the gentleman's agreement was if we thought we had possibly made the same discovery at the same time, we would try to coordinate publications. So when we knew the oxygen sensing mechanism, I reached out to Patrick Maxwell, not completely understanding that he was still a trainee in Peter's lab. So at that point he said, you really need to speak with my mentor, Peter Ratcliffe. This was about the year 2000. We had not met up until that point. So I called Peter. Now, I think you can understand, I didn't want to deprive him of making the discovery independently of me, nor did I frankly want to give him all the answers if he hadn't. So I think we did this thing that could variably be called the dance of the seven veils, or flipping one card at a time. Does it smell like this is the answer? Does it rhyme with that? And then we finally figured out we had the same answer, and we agreed to co-publish.
It was quite an interesting thing, because actually we didn't have the complete answer. And neither of us knew who had the complete answer. We both had the same incomplete answer at that time. That's fair to say. We had one site out of two, and we didn't have the enzymes, although it was implicit in what we had that there was a mechanism of oxygen sensing. So it was a key step where we worked on the most studied part of HIV, so perhaps it wasn't coincidental that we came by the same findings at that time.
Yeah, but just for the non-scientist, I think the metaphor would be in science, you're going along and you're really doing one mosaic tile at a time. So when Peter says it wasn't complete, of course science is never complete, there's always remaining questions, but this turned out to be a particularly shiny and satisfying tile to put into the picture, and it's the reason why we were in Stockholm, I think it's fair to say, last month. So.
Your discovery has also been praised for paving the way for new strategies to fight anemia, cancer, and other diseases. Could you tell us about how exactly what you discovered can be used to fight against these diseases?
Yeah, to be clear, we got the Nobel Prize in Physiology or Medicine. They hedged their bets, and it's still a bit unclear, the medicine bit. We've made a physiological discovery, which is how your body works, and we believe it's an important one, and that's pretty clearly achieved. Now the medicine, it turns out that this oxygen sensing enzyme has what is called a co-substrate. This is a small molecule that it uses in its mechanism. So that's an ideal drug target, because the chemists can make what's called an analog of that co-substrate, block the thing, mimics hypoxia, makes the body think it's hypoxic when it isn't, and trains the adaptive response somewhat before it's fully necessary, and hopefully that gives the adaptive process an advantage. And those are the drugs being used to treat anemia, and they're looking pretty good. But of course we're both doctors, and there'll be medical students out there who know that a new medicine always entrains risk. So it will be 5 or 10 years before we're really sure that this is a transforming medicine, or whether it was a good shot. The flip side, which Bill might fill us in on a bit more, is the cancer, kidney cancer, where you might want to do the reverse. I don't know if that's looking promising as well.
That does look promising. So in a nutshell, all cancers need to obtain oxygen, and particularly in kidney cancer, this pathway we help to define is the pathway that's been co-opted or hijacked. So we now have new drugs that directly or indirectly block this pathway. Some are approved. They largely work indirectly on a protein called VEGF. But there are now drugs that work on the master regulator, HIF, that look very promising as well. And as Peter mentioned, in diseases where you want to promote oxygen delivery, we have a new class of drugs that do look promising, that basically trick the body into thinking it's at high altitude, and you start making appropriate changes on that basis. I completely agree with Peter. On the other hand, I have a colleague who says, if you're smart enough, you can always think of a reason why an experiment will fail. And likewise, if you're smart enough, you can always think of a reason why a drug will eventually become toxic. So Peter and I are well aware of the fact that these drugs on further review might become toxic as they're used in millions of people over time. One sort of encouraging note, at least with respect to these HIF stabilizers, these drugs that promote oxygen delivery, is even before they were approved, certain professional athletes were obtaining the chemical from Chinese chemical manufacturers and were ingesting it prior to, for example, their bike races. And since most of them don't have PhDs in pharmacology, I think that suggests this will be a fairly forgiving drug in terms of dose and exposure.
Yeah, we know that it's pretty safe in the short term. The problem for medicine is when you want to use something for 10 years, then of course all sorts of unexpected good things could come about. It could be highly protective against heart disease or other things that are suffered by the patients, usually kidney patients that have this EPO deficient anemia. They're also predisposed to heart attacks and circulatory problems, and that will be fantastic if it turns out, and there are theoretical reasons why it might turn out that the drugs are protective against those things. They might also be protective against progressive kidney failure. That would be terrific. But there's a large element of empiricism in drug development. People will go on about precision medicine, that molecular biology can deliver you exactly what you want, the magic bullet. We can and have delivered a drug target. It's then a question of dose and careful, painstaking trialing to work out just where the benefit is and where the risks are in using that medicine.
And my final question before moving on to the audience is, what's next for both of you? If you can tell us, what are you working on now? Are you going further into this area, moving on to something new? If you can tell us, that would be great.
Yes, Peter, what are you working on right now?
I think we'll be going our separate ways probably. So I alluded to those things that were insoluble problems in the late 19th, early 20th century. Control of breathing. Now, we have not got this. What we've worked on is a system that takes hours to days to operate. Can't operate on a very short term because it uses gene expression. So I would like to work on shorter term responses, and I'm sort of rejigging the lab that way.
So one of our major areas of interest, the cure or control of AIDS, and before it, tuberculosis, required combining drugs that had distinct mechanisms of action to sort of prevent resistance from emerging. The idea being that if the virus or mycobacteria had figured out a workaround against one drug, you would still be using two perhaps other active drugs. And so by using combinations of drugs, you would be able to control these diseases. And the same principle applies in cancer. So in kidney cancer, which is one of my focuses, we're trying to find other targets and hence other drugs that can now be combined with these new HIF modulators and VEGF modulators we talked about a moment ago. So eventually we'll be treating those patients with hopefully 3 or 4 active drugs that have distinct mechanisms of action, and we'll get around the resistance problem.
So we'll move on to questions from the audience now. If you have a question, please raise your hand in the air, wait for the microphone to come to you, and then stand up when asking your question. Could we go to the hand in the second row over there?
Hi, my name's Kumaran Govender. I'm a default student here in clinical medicine. So I've got 2 short questions. The first question is that, how would you say your medical career kind of informed your questions in a basic science kind of form? And do you think that was really important that you went through that clinical training and specialized? And the second question is, in your career, when did you realize that perhaps the work you were doing was actually worth the Nobel? I mean, I guess you were really prominent at the time, publishing in Nature Science, but when did it actually strike you that this is actually groundbreaking?
So I've already mentioned that I think my clinical training helped me a great deal in terms of understanding or guessing, if you will, that the VHL gene would be a good problem to work on and would teach us about kidney cancer and angiogenesis and oxygen sensing. But I think the other way that my clinical training helped me is, clinicians get bombarded every day with lots of information, and they have to use that information to sometimes make life or death decisions. And so if every piece of data is pointing you in the same direction, it's easy, but oftentimes on the wards that's not the case. And then you have to attach relative weights to the different pieces of data and then make your decision. And that turned out to be very helpful for me when I started working in the laboratory, because likewise in science and in the laboratory, you might do 10 experiments and maybe 8 point you in one direction, but 2 point you in another direction. And frankly, sometimes it's those 2 that are actually the correct indicators. And so you have to start to process and have some sense of, well, which experiments can be misleading and why. And I say that because I occasionally meet very bright people in the laboratory who just completely get immobilized if they are dealing with conflicting data. So it's a forest versus the trees sort of problem.
The integration thing is similar between the diagnostic process. I'll just say one thing is different. You might like this. In clinical medicine, if you don't know what to do nothing. In the lab, if you don't know what to do something. There's a reason for that the clinical experiment is ongoing before your eyes, and you just simply observe is the equivalent of doing the experiment. Of course, in the lab, you don't do the experiment, nothing happens at all. So that is different, but otherwise the process of integrating all sorts of conflicting data, as Bill said, is not dissimilar.
And I think the member's second question was, when did you realize that?
So I often tell people you have to take some pride and joy in the small victories along the way, because there's certainly many frustrations. But I think the day we understood that HIP was hydroxylated and we looked at the mechanism and it struck us as simple and beautiful and elegant, it was very clear that was going to be sort of once in a decade, maybe even once in a lifetime discovery. Which also brings up the point that I think Peter and I agree on, is what people have to understand is we discovered the mechanism. Had the mechanism turned out to be inelegant or clunky or the 20th example of blah, 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 there wouldn't have been a trip to Stockholm. And so when you make the discovery, whether the discovery is beautiful or not is a tribute to nature. It's not a tribute to the discoverers. But certainly, at least when I saw that result, and I think Peter would agree, we knew that was something special.
Yeah, I think there were about 4, maybe 5 times when there was that so-called Eureka moment. It was nothing to do with brilliance, and to be honest, on some of them I was a little bit puzzled when I first saw the radiograph. But those are the moments that you live for, and actually it's rather surprising to be going to Stockholm with all the celebrations. About 19 years later on, nothing's actually changed. It was those moments that were the enormous high when, of course, most things go wrong, so that's you get used to that. But I guess about 4 times in a period of 12 years we had one of those things.
Is there another question? Could we go to the hand in the back? Yeah.
One thing that Bill mentioned in the introductory remarks was that you grew up in an age of bipartisan support for science and education, and I'd just be interested in both of your reflections in the age of the 21st century news cycle and 21st century politics and the context of economic rationalism in universities. What do you view your roles as Nobel Prize winners, and if you view that you have a role in advocacy for that kind of approach and for education moving forward today?
So, I think when you win the Nobel Prize, it gives you a pause and you reflect, as I tried to do a little bit, what kind of things mattered. Now, I will confess, I had no interest in policy or policy making throughout my entire life. I was glad that there were people who did it, and occasionally I voted for them, but and likewise, I've avoided leadership positions and administrative positions. I just wanted to either do my clinical work or just wanted to do my science, but I now completely appreciate that policy really, really matters, and I was the beneficiary of a lot of wise decisions that got made when I was a younger person. And I do fear for our future, because I mentioned, scientists and engineers were the good guys. They were the heroes. I never thought I would live to see the day where in certain quarters, scientists and engineers could be so easily disparaged if what they were trying to tell policymakers didn't fit with their current political narrative. Think about things like climate change. I thought if nothing else we could agree that it was a good idea to make policy based on things that are objectifiably true and testable, as opposed to just pulling things out of thin air. So I think if we're not very careful, I mean, I don't want to overstate this, but some people have said, this is a path to the dark ages. We can either believe in truth and data and reason, or we can just make stuff up if it's expedient to do so. So I think, unfortunately, we all have to get more involved in the political process. I know I was not as involved as I maybe will now need to be as a Nobel laureate, and it's actually one of the few things I'm actually looking forward to, in a sense that now I have this new soapbox or celebrity status that maybe people will listen to me who wouldn't have listened to me before. One of the questions one of the questions at the Nobel Minds with this TV show they did was, are you now willing to meet with policymakers? And of course we all said yes, but my answer was, I think in many cases a better use of my time will be to meet with the voters who are going to replace them.
Yeah, I don't know. My answer would be yes, I do want to do something different. I would like to speak up for education, actually. I can understand why we'll pay more money to a doctor or a lawyer, for that matter, than a teacher. That's because I've had my education and I might need my health care or my money to be looked after or whatever. But I cannot, for the life of me, see why society should make that decision. Why is teaching as a profession, in my view, seriously undervalued? And what we've done probably owes to the teaching I received in Northern Grammar School 50 years ago. I think the university undervalues teaching. It's of course easy to say this with the research success, but I think both society and the university undervalue it. I'll just give you one observation. Because teaching is facing a growing challenge of how to manage people to the frontier of knowledge. We had another piece of good fortune. A week after the announcement from Stockholm, my daughter was on the phone, or at least her partner was, to say she'd had a little baby. So our granddaughter was born. She's a lovely little girl. That girl, she knows absolutely no molecular biology whatsoever. She doesn't even know the periodic table. She doesn't know mass balance. She knows nothing whatsoever. And the little girl, she has to learn all this stuff, and then on top of it, what has been discovered over the 40 years or 50 years or 60 years since you or I were that age. So this is an extraordinary challenge which I don't think has been thought through. How do we keep the society bringing up all these new human beings to the frontier of knowledge? And in a sense, we're like an army that's extended its supply lines a little bit thoughtlessly. So I would like to make that argument to the people who matter in making these decisions. I believe that education is undervalued, seriously undervalued by society, and we're all guilty, including this university, of that undervaluing of teaching. So I'd like to use my little influence on that one.
Could we go to the hand over there, please?
Thank you for the wonderful talk. My question is about publication. This may be primitive. However, if the finding is so innovative, different from the current finding, you may have some resistance from the so-called authority. So in your case, how can you overcome those barriers or obstacles? Do you have any advice for the young researchers?
So the question relates to, especially if you've discovered something new, unexpected, how do you deal with the publication process? because you can almost be sure you're going to get some pushback. And in our case with the HIF hydroxylation paper, it was the case that at least one of the reviewers laid out all the reasons why we had to be wrong. And then the editorial board initially thought, well, we'd like to see the next step, and et cetera. And so it wasn't a given that even these two now, I think, fairly famous papers were going to be accepted. Fortunately, there was a very strong editor, however, who intervened on our behalf. First of all, she said, okay, there's always going to be a next step, but it's a good thing if we publish this, because then everyone could be trying to do the next step and not just Drs. Radcliffe and Kaelin. And she also realized that the one reviewer who thought we were wrong had sort of absolute tunnel vision and didn't understand that it was precisely because we were publishing something that was contrary to dogma that it was important. But I think we are in this sort of arms race now where papers now contain too many claims, too much data, and I think we have to go back to making papers a little bit simpler, fewer claims, but more lines of evidence to support those claims. And we have to get away from attaching so much artificial significance to whether you published in the very top tier journals, because that distorts the whole publication system.
Yeah, no, it's a real problem. I think there is enough. The editors have an easier job if there are two papers. And I suspect the fact that there were two papers helped to persuade them that this is very likely to be true and very likely to be important. But that was almost my first experience of an editorial position being overcome. I think that was largely courtesy of Bill that it was overcome. But as he said, she was a very able editor, and I think that mattered. Prior to that, we'd had all sorts of trouble. We were reasonably sure we were onto something important, but we couldn't get the editors to see it that way. But I think this is very important. This is the whole of a research career is about finding things out. It's not about publishing in this, that, and the other. And somehow that's got completely out of hand, the prestige of publishing in one place rather than another. Nothing to do with the science at all. Should never be considered.
But Peter also brings up one very important point. I've been impressed over and over how many times it's been true in my life that doing what I thought was the right thing also turned out to be the right thing. So I thought it was the right thing for us to co-publish, but as Peter said, effectively that helped, I think, get the papers published because we had sort of simultaneous, sort of confirmation or corroboration.
Thank you. We have time for one more question. If we could go to the hand right here.
Hi. I was just wondering, just one simple question, I guess. What do you think about publishing negative data?
Well, we've just done that. We have a paper which is negative data. I'm very fortunate. I have quite strong funding, so the first point is only my lab could have published that paper. Most labs couldn't afford to do it. So the publishing of negative data, the doing of experiments that have negative results is extremely important. But it's extremely difficult to persuade your funders that this is a good idea, and it's extremely difficult to persuade editors that it's a good idea to publish it. But I can't for the life of me see why the bias is so strong. I mean, we have to achieve an answer to a question, and that means seeing both sides of the argument with equal weight. But yes, you're right, it is extremely asymmetric in terms of a publication bias to positive results, and that is causing all sorts of trouble.
We do have time for one more question because that one was quite short. Could we go to the hand over here?
Good evening, thank you for your speech. I've got one quite specific question concerning bone cancer. Is there any way for early diagnosis of bone cancer except for the X-ray diagnosis of the whole body? Thank you.
Yeah. So you're correct that there are fairly powerful imaging tools now for looking for early lung cancers, but people are also working now on things such as circulating DNA, looking for a mutational signature in the blood that might indicate that someone has an early lung cancer. The problem is going to be, however, I can tell you this with certainty, that even with prostate cancer and breast cancer, where we've done early screening for quite some time, you have to diagnose currently many people who frankly never would have run into clinical problems with their early cancer to capture those few people where you've actually now saved their life. So we're probably over-diagnosing with the current tools many people who have early stage prostate cancer and early stage breast cancer, and it will certainly be true for these other cancers as we get more and more of these screening technologies, that we may be over-diagnosing people. So we have to make sure that we get smart and can tell which of these tumors would go on to be a problem over time and which would not.
Yeah, the problem with cancer, biologically, you almost can't make it. The cancer has to evade all sorts of mechanisms concerned with how the cell detects trouble. Very few cells get through. So you will find that there will be cells with the same mutational background that, for whatever reason, don't achieve that escape. It'll be very difficult to distinguish those that do from those that don't. So even if you saw circulating tumor DNA with this mutation, it doesn't mean that in the context it's occurred, you're going to develop a cancer. So it will be a really difficult problem.
Thank you so much. That's unfortunately all we have time for today, but please join me in thanking Drs. Kaelin and Ratcliffe for being here today.